Thank you very much, Shannon. I'm Kazuki Shibanuma from the University of Tokyo, Japan. Today, I will talk about a particular prediction framework for steels based on multiscale modeling of crack rules. So let's start. Okay. And this slide shows the table of contents of this presentation. I will show you the research background first. Research background. So, how can we predict fatigue life? We know several dominant factors to determine fatigue life. First one is microstructure. And monotonic tensile properties also has strong correlation with fatigue life. And of course, the loading condition affected. So based on this information, we should be able to predict fatigue life. However, the quantitative relationship among them has not been clarified yet. So the purpose of this work is to solve this very basic issue by establishing multi-scale modeling strategy. That is the purpose of this work. So next, I will show you the modeling basis based on experimental observation, which is most important part of this presentation, though it's not numerical work, but experimental work. This slide shows the test and observation conditions. Using an ordinary Marius field, we perform tension compression test using smooth specimen like this. And we observed crack initiation growth process using high magnification camera. And this slide shows the observation results. The final number cycle to failure was about 220,000 cycles. It's typical ordinary high cycle fatigue condition. So this photo is a crack initiation site. 0 cycle, 2,000 cycle, 5,000 cycle, 10,000 cycle, 100,000 cycle, and 210,000 cycle. It's just before failure. So we can see crack initiation and growth from here. So of course, at 0 cycle, we can see nothing. However, at only 2,000 cycle, a crack was clearly observed, even though it was less than 1% of the fatigue life. So it indicates that a crack initiation life does not exist or is ignorable, at least this kind of kinetic still. In addition, from the last photo, we can see that the damage caused by the activation of the multiple slip systems clearly increased after the crack passed the fast growing boundary. So the stage 1 boundary between stage 1 and stage 2 may be defined by the first grain boundary like this. So we developed a model based on these experimental facts. So I will show you the outline of the model presentation. This slide shows the modeling concept. And the first one is the calculation on fatigue life. Based on the experimental observation, it was difficult to define crack initiation life, though it is very common approach for predicting fatigue life, evaluation of the fatigue life. But we ignore it. The entire fatigue life is estimated only from crack growth life. This is most important concept of our model. And the second one is the required input data. As I mentioned in introduction part, the microstructure information, motor tensile properties, and loading condition should be dominant factors to determine the fatigue life. So we use these information as the input data. And we don't use any adjustable fitting parameters. And we don't need any preliminary fatigue test data or target still. So it means we provide pure prediction. And the third one is the division dimension problem. Actually, the fatigue crack initiation growth is very complicated 3D phenomenon. However, we already know some characteristic features, such as a crack generally initiates at the surface, and the crack growth direction is approximately orthogonal to that of the maximum principal stress. So, we developed a model, a 3D simulation by describing 2D problem with two steps. And the last one is multiscale model synthesis, which is an approach integrating multiple models with large-scale differences. So this slide shows the outlines of the proposed model. This model is composed of three sub-models: macroscopic finite element analysis, the microstructure, and crack growth. I will show you the outline of these respective sub-models. The first one is macroscopic finite element analysis. The role of this macroscopic finite element analysis is a calculation of strain amplitude field and definition of an active zone. As a cyclic stress strain relationship, we employ the empirical formula by Lee et al. And using this formula, we can estimate cyclic stress strain relationship based on only monotonic tensile properties. And then we define the active zone as a surface domain based on the strain distribution. And this active zone is a evaluation domain for other submodels. And then next one is a microstructure model. And as I mentioned, we assume 2D problem with two steps. So this 2D assumption makes significant simplification of microstructure model. As a geometry of ferrite grains and parallel columns, we assume simple ellipses or rectangle like this, based on the size distribution of the microstructure. And this slide shows the special grain distribution in surface grain. The active zone is divided into surface elements, and we assign each grains into each surface elements like this. And all grains are assigned in this surface element are assumed as a possible crack initiation sites. This is our first 2D problem. And the special grain distribution in inside plane is modeled corresponding to the crack shape transition as shown in these green lines. And we assign grain on each lines, and the thickness is averaged. And then we obtained the special grain distribution in inside plane like this. That is a microstructure model. It's very simple. And last model is crack growth. Based on the observation results, we predict fatigue life based on crack growth simulation only. So for this purpose, we employ the interaction theory between crack and grain boundary as a basic theory. This theory is described by these equations, but I will not explain the detail today. So anyway, using this model, using the information about grain sizes, friction strength to dislocations, and the effective shear stress as the input data, we can obtain dislocation density ahead of the crack tip, slip length, crack tip slightly decelerated range, crack growth rate, and fatigue life as output data. So to perform this simulation, we need three kinds of input data. But grain sizes can be obtained from microstructure model. So we have to evaluate friction strength to move dislocations and effective shear stress. The friction strength to move dislocations is a kind of material resistance in this model. And its physical meaning is same with yield shear strength of single crystal. So we can estimate it based on Hall law. Friction strengths of H phases, ferrite and pyrite can be obtained, can be separated based on linear mixture rule like this. And the effective shear stress is a kind of driving force in this model. But evaluation process of this parameter is a little bit more complicated, so I will show you only outline. First, we evaluate the equivalent stress tensor, which is corresponding to the total strain tensor obtained from finite element analysis. And considering the effect of the crack shape, strain distribution, and crack opening closure behavior, we evaluate effectively most stress tensor range. And then considering the SIP system of BCC crystal, we evaluate effective shear stress based on these expressions. So, and this slide shows the evaluation process of the fatigue life. The crack initiation is assumed from all the grain assigned in the active zone. And then the grain lines are normalized, and effective shear stress is calculated for all combination of the adjacent grains like this. And then the ratio between friction strength and effective shear stress is averaged. By applying the interaction theory between crack and grain boundaries, we can obtain the number of cycles to failure from each crack initiation site. The fatigue life of structure or specimen can be evaluated as a minimum number of cycles to failure calculated from all the crack initiation sites. That is a kind of weakest link assumption of this model. And then I will show you the strict validation. So we employ three kinds of steel. We can see wide range of the variation of the chemical composition and strengths and grain sizes. And these are the information of the size distribution of the microstructures. We use these information as the input data. And we perform a fatigue test using these four specimens. A smooth tension compression test and 3-point bending test with star notch specimen and sharp notch specimen, and the fatigue test to observe practice behavior. So we employ 3 types of steel and 4 types of specimen. As a total, we perform 10 types of the fatigue test. And this slide shows our experimental results of the SN curve. So steel A and B and C, and each graph has various fatigue test data from different specimen shape. So we can see sufficiently wide variation of the results. But now there is a set of parameters we cannot determine beforehand, and that is the constancy in crack loose load. So we identify these 3 parameters using the results of the smooth tension compression test with steel A. This is the red plot, like this. So we can see very good agreement with experimental results, but note that this is just fitting, not predictions. Now we identified all the parameters, so there are no any adjustable fitting parameters anymore. But we have 9 SN curve other than this data plots. So we try to predict these SN curves using same parameter setting. And these are the results. So we can see that the proposed model could successfully predict all of the experiments. And these results indicate that the fatigue life of steel can be predicted only from crack loose life. So maybe due to the time limitation, I will skip the summary part. So, but I want to introduce this only. It's a possible collaboration in co-shared. If you are interested in our work, I'm very happy to discuss collaborative opportunity. So our Python source code or multiscale model can be shared upon your request. So please feel free to contact me. That's all my presentation. Thank you very much.